Hello, my name is Wentao, and I'm excited to introduce our work, DeepGMR, Learning Latent Gaussian Mixture Models for Registration. This work is done in collaboration with Ben, Kiwang, Varun, Dieter, and Yang. Deep Gaussian Mixture Registration, or DeepGMR in short, is a novel point cloud registration algorithm that integrates 3D deep learning with probabilistic inference. Given two misaligned point clouds, it tries to recover the ground truth transformation by maximizing the likelihood of the inputs under a learned Gaussian mixture distribution. Point cloud registration is a long-standing problem in 3D computer vision, with important applications in graphics and robotics. There are a wide variety of registration algorithms with their respective advantages. However, almost all existing registration methods suffer from one or more of the limitations listed here. For example, methods like ICP and HGMR are local, meaning that they will likely fail if the transformation between inputs is large. To overcome these limitations, we propose DeepGMR, a point cloud registration algorithm that is accurate and efficient at the same time, works without any initialization, and is robust to noise. In addition, DeepGMR is entirely differentiable, making it a handy module for gradient-based optimization. On a high level, DeepGMR consists of two stages: a data association stage that estimates correspondences from input point clouds, and an optimization stage which computes a rigid transformation from estimated correspondences. This is a common design for many registration algorithms. However, estimating correct correspondences can be very challenging. As a result, some methods iterate between the two stages, hoping to converge to a local optimum, while other methods use sophisticated techniques in the optimization stage, such as mixed integer programming, to identify inlier correspondences. But these existing solutions have negative impact on the accuracy or speed of registration. In contrast, DeepGMR performs robust and accurate data association by employing a novel representation of correspondences. Specifically, instead of estimating direct correspondences between input points, DeepGMR assumes the input point clouds are samples from the same latent Gaussian mixture model and estimates the correspondences between input points and the Gaussian mixture components via a learnable network. This not only removes the need for iterative procedure, but also reduces the optimization stage to a system of equations that can be solved in closed form with differentiable compute blocks. Now let's take a deeper look at the correspondence network and the two differentiable compute blocks. The correspondence network takes a single point cloud with endpoints and outputs J-scores for each point, which represent the expected probability that a particular point corresponds to a particular component of the latent Gaussian mixture model. Although we used PointNet in our experiments, in practice, PointNet can be replaced with any 3D segmentation network. The key is not in the network architecture, but in how the output is interpreted in the compute blocks that follow. The first compute block, denoted mtheta, takes the output of the correspondence network and computes the parameters of the latent Gaussian mixture model, including mixture weights, component means, and covariances. Given the correspondences between input points and the GMM components, the maximum likelihood parameters can be computed in closed form using the equations shown here. In fact, the correspondence network and mtheta compute block forms a single step of the expectation maximization algorithm, commonly used for fitting GMMs. Please see our paper for more details on the connection between DeepGMR and classical GMM-based registration. The second compute block, denoted MT, computes the rigid transformation parameters, i.e. 3D rotation and translation, using the GMM parameters estimated by mtheta. Note that the correspondence network and the mtheta compute block compute two sets of GMM parameters independently from the source and target point clouds. There is no explicit constraints forcing them to be the same distribution. Nonetheless, the MT compute block treats the target GMM as a transformed copy of the source GMM and solves for the transformation that best aligns corresponding GMM components. In this way, consistency between the two GMMs will be implicitly enforced, because the correct transformation can only be computed if the source and target GMM are transformed copies of the same distribution. Note that our formulation allows the transformation to be solved with a single SVD decomposition of a J by J matrix, where J is the number of GMM components, which is extremely efficient. We evaluate DeepGMR and baselines on two datasets. The ModelNet dataset contains synthetic point clouds sampled from 3D CAD models, while the ICL NUIM dataset contains real-world point clouds from indoor depth scans. In order to test robustness to noise and generalizability, we generate three variations of the ModelNet data, which contain clean point clouds, noisy point clouds, and point clouds from categories unseen during training. We use two metrics for evaluation. The RMSE metric is designed for evaluating registration algorithms in the context of scene reconstruction. Specifically, it measures the root mean squared distance between a point cloud under the predicted transformation and the same point cloud under the ground truth transformation. The recall metric measures the percentage of test instances whose RMSE is below an acceptable threshold, which is set to 0.2 in our evaluation. The table shown here summarizes the results. Compared against state-of-the-art geometry-based as well as learning-based registration baselines, DeepGMR achieves lower average RMSE and higher recall across a variety of data settings. The only methods that are able to match DeepGMR's performance are over 1,000 times slower on average. In addition to accuracy, DeepGMR also achieves notable efficiency improvements over baseline methods. This makes DeepGMR a suitable candidate for applications that require a point cloud registration algorithm that runs on the order of tens of milliseconds per instance. Despite being accurate and efficient, DeepGMR is not without limitations. An implicit assumption made in the formulation of DeepGMR is that the source and target point clouds are IID samples from the same underlying distribution, which may not hold for point cloud pairs with partial overlap. While it is possible to lift that assumption, we leave the investigation for future work. Please refer to the supplementary material for an evaluation on the registration of partially overlapping point clouds and a more in-depth discussion. In conclusion, DeepGMR provides a principled way of integrating 3D neural networks inside a probabilistic registration paradigm. We believe DeepGMR can be useful for applications that require accurate and efficient global alignment of 3D data, and hope that it can inspire future research into learning-based probabilistic registration.